Hello humans, my name is Professor Leach, and today we are going to talk about reading expressions with radicals, and also a little bit of simplifying expressions with radicals. So, since we're doing things with radicals, I brought along as a guest Mr. Bernie Sanders. I'm just kidding. Bernie Sanders is not radical at all. He just thinks humans should be treated decently. I know in the United States that's a radical idea, but really, there are no radical leftists in the United States. Not in office anyway. So that was just, so let's talk about reading expressions with radicals. And what I mean by radicals actually is this symbol, this radical symbol. Last time we talked about this index being the radical, being the denominator of the exponent. The index of the radical is the denominator of the exponent. The index of the radical is the denominator of the exponent. So the reason that we are introducing radicals now and not way later in the book, as is tradition, is that I want to get the idea across that radicals are just exponents. Radicals are just a kind of exponents. Radicals are just a kind of exponent. The index of the radical is the denominator of the exponent. That's how we go from radical notation to exponential notation. So what we want to be able to do is to look at an expression. For example, let's say the cube root of 2x minus 5, and I know I keep using 2, 5, and then some exponent involving a 3. And we want to read the order of operations. What happened to the x and in what order, in the same way that we read the order of operations when we had multiplication, just regular exponents, non-radical exponents. So we do the same thing. We can come up with the order of things that we're doing. First, we're multiplying x by 2. I'm going to use our standard notation, our standard, oops. Second, we subtract the 5. And then third, we do the cube roots. So we can either say the cube roots, or we can say raised to the 1/3 power. So here's our shorthand for a shorthand description for what's going on in this expression. We want to distinguish this. Oh, no, we don't. So we want to make sure that we know how to read the radical. And in a radical, the horizontal bar acts as a grouping symbol. So that tells you where the parentheses should go. So the radical's horizontal, the horizontal line of the radical tells you where the parentheses will go. So the horizontal line of the radical tells us where the parentheses go. The best way to practice this is to convert the radical to exponential notation. So as an exponential notation, in exponential notation, we would take in parentheses 2x minus 5 and raise that to the 1/3 power. Here we have it in single line syntax. And it reads the same as the radical expression. First, we multiply by 2. Second, we subtract 5. And third, we raise to the 1/3 power. Want to make sure that when we're raising to a fraction exponent, that the fraction exponent shows up in parentheses. Always put your fraction exponents in parentheses. Always write your fraction exponents in parentheses. It helps increase clarity of what you're writing. So a note to writing fractions in parentheses. Usually when we have a fraction exponent, if we're writing it as a superscript, we should use side-to-side notation. We should use single line fractions in a single line syntax. So if I want to say write x to the 1/3 power, an option for writing this can be written with a superscript. As x, and then we have to make it very clear that we're making a superscript, and then we use 1/3 power. When we write fraction exponents with a superscript, we should definitely write side to side, not diagonal and not up and down. We use the single line version of the fraction. We should use a single line for fraction exponents. This is better than diagonal exponents. So here's a single line fraction. Sorry, not single diagonal exponents, diagonal fractions. We can write fractions in a lot of different ways. We have this single line version. We have this vertical orientation. So maybe we could think of this as horizontal. So we can have fractions as a single line. So that's a horizontal orientation. We can write 1/3 and write this vertical orientation. Another common way we write fractions is on a diagonal. When we're writing math, I can't recommend against diagonal orientation enough. Don't use this one. Maybe your next math teacher will be absolutely huge fan of diagonal oriented fractions, and they say, oh man, this just looks the best. Don't do it in my class. This is just one of the idiosyncrasies that you have to deal with when you are in my particular class. I don't like fractions written in diagonal orientation. It makes things look like they're in the denominator, and it really makes things strongly look like they're in the denominator. So if we have, say, in vertical orientation, we would write 1/3 x. In single line orientation, we could write 1/3 x, or we could write just x/3, which would even be better. That with parentheses is kind of meh. Diagonal orientation is just bad. If you write 1/3 x, looks like 1/3x, which is not what we were trying to write. Diagonal orientation is bad. Don't use it. So diagonally oriented fractions is bad. Don't use it. We got better ways of writing things. The best practice is to put fractions in parentheses. It's different. The way we write things tends to be different when we have fraction multiples of variables. So with variables, we tend to favor things like x/3, especially if we're going to shove things into a single line. We could also write this as 1/3 x as x/3. It depends on what we're trying to do, right? A compact little statement, or if we're really if we really are playing with the coefficients and the variables. It kind of depends on what we're doing. Ultimately, it doesn't matter what we're doing, but except for this is bad. Actually, it's worse than bad, it's horrifying. Any questions? And this goes double for exponents. If we're trying to take a fraction and shove it into an exponent, a vertical orientation is too hard to fit into an exponent. Horizontal orientation is best for fraction exponents. Vertical orientation, it looks too much like x and a third. So if we have a base like 2 to the 1/3 power, we could write this as 2 to the 1/3 power. That looks fine. It's clearly an exponent because it's small and it's a superscript. But if we try to write this fraction exponents in a vertical orientation, it takes up a lot of space. It's clear until we start getting sloppy with the 1/3, and it'll look too much like 2 and 1/3. So are we saying 2 to the 1/3, or are we saying 2 and 1/3, which means 2 plus 1/3? And in every scenario, diagonal orientation looks bad. Any questions? All right, that was a little bit rambly. What we're trying to do is read radicals as exponents, specifically fraction exponents, and that's why we want to talk about them now. We want to read radicals as exponents. So the other thing that we want to do today is talk about simplifying radical expressions. All right, so we can simplify radical expressions because we're going by treating them as exponents. Radicals are exponents. That's the key thing. Radicals are exponents. So we want to think, when we see radicals, we want to think of them as exponents so that we know what rules to apply. Exponents represent repeated multiplication, which is weird in this case because they're fractions. Exponents go before multiplication, unless parentheses. And if there are parentheses, exponents distribute over multiplication. Those are the things that we want to think of. Radicals are exponents. So exponents, radicals before multiplication, unless parentheses. Exponents distribute over multiplication. So radicals distribute over multiplication. So what does that mean for us? What does this mean in terms of problems? If I ask you to simplify something like the square root of 25 x to the 8th, the number part is familiar to us. The square root of 25 is 5. Then we need to take the square root of x to the 8th, and we want to imagine the square root as a 1/2 power. But what we're doing when we do that is thinking of the radical as an exponent, and using the distributive property to distribute the distributive property of exponents over multiplication, and applying the radical to each factor in the multiplication. So what we want to do is, the way we would naturally read this is we'll take the square root of 25 is 5. The square root of 25 is 5. And the square root of x to the 8th is x to the 4th. If we think about the square root of x to the 8th, this is an x to the 8th raised to the 1/2 power. And when we have something with an exponent raised to another exponent, we can multiply the exponents. And now we have simplified the expression. So in terms of what we're learning new, we read the square root of x to the 8th as a 1/2 power. The index of the radical, the invisible index, is a 2. The index of the radical is the denominator of the exponent. When we raise an exponent to an exponent, we multiply the exponents. This is a variation of x squared to the 3rd is x to the 2 times 3, which is x to the 6th. We're using that same rule. It's just that now one of these things is a fraction. This rule made sense because I just wrote 3 copies of x squared, and each squared was 2 x's. So I had 6 x's all multiplied together, and we write that as x to the 6th because exponents are repeated multiplication. Once we started writing fractions in our exponents, that rule kind of got a little bit weird. How do I multiply 1/2 of a thing? Well, now we can see a 1/2 exponent is a square root. The other thing that we're doing is we're using the distributive property, and we tend to do these things automatically, but we want to think about them carefully now. So the other thing that we did was we thought of this as doing the square root of 25 times the square root of x to the 8th. So when we just take a factor at a time, we are using the distributive property. We're distributing the 1/2 power to the 2 factors, 25 and x to the 8th. So here we are doing a distribute. We do this because the radical is an exponent, and exponents distribute over multiplication. So for this step here, any questions? The reason that I talk about these things this way is that I don't want radicals to be some extra thing. Radicals are just some other kind of exponent. So however we would treat this with an exponent, that's what we do with the radicals. And it's the same thing. If, for example, I had, let's say, 3x to the 5th all squared, I know that we would simplify this as 3 squared, which is 9, and x to the 5th squared is x to the 10th. And when we simplify we simplify the square of the product of 3 and the 5th power of x and come up with 9x to the 10th, we're applying the same principles as when we simplified the square root of 25x to the 8th. We distributed the exponents. We do 3 squared and x to the 5th squared. And we're doing this not because these are the rules that have been set up for dealing with radicals and exponents. We do this because this is how numbers behave. This is what the numbers do. We're just trying to figure out how to write that, how we can express that. Not fancy rules. I'm not trying to be mean. This is just how numbers behave. If you want to come up with your own number system where numbers behave differently, then that's fine. This is how numbers work. If we want our numbers to do the basic thing of like counting, then this is how they behave. Comments? Deep thoughts? So that's the way I want you to approach these radical expressions. There's a quiz up on the old campus that has you simplifying expressions with simplifying radical expressions. I want you to treat those expressions as they were those radicals as they were exponents with an appropriate denominator. So for example, if I had you find the cube root, if I wanted the cube root of, let's say 8 x to the 12th y to the 21st. We want to imagine the cube root as a 1/3 exponent. So a cube root is a 1/3 exponent. So first thing I want you to think of is imagine this as 8 x to the 12th y to the 21 raised to the 1/3 power. And then just break this into pieces. The cube root of 8 is 2, because 2 to the times 2 times 2 is 8. So 2 times 2 times 2 is 8. So the cube root of 8 is 2. Then for the exponents, the index of the radical is the denominator of the exponent. So this is x to the 12 over 3 and y to the 21 over 3. So the cube root of 8 is 2. X to the 12 over 3 is x to the 4. And y to the 21 over 3 is y to the 7. The index of the radical is the denominator of the exponent. The index of the radical is the denominator of the exponent. All we're doing is the distributive property. So this is going to be an 8 to the 1/3 power times x to the 12 over 3 and y to the 21 over 3, because the index of the radical is the denominator of the exponent. Index of radical, purple. Index of radical is denominator of the exponent. Any questions? Comments? Deep thoughts? Snide remarks? All right, so get going on quiz 2.3, simplifying radical expressions. I know this is coming out of order because we were reading expressions and then I introduced the radicals. And then so this is kind of jumping the gun in front of the simplifying expressions. But it's better to start early than to start late, like in the last chapter. We'll look more at more simplifying of radical expressions and what's going to be left over. But the rule for all of this is going to be the index of the radical is the denominator of the exponent. We're just applying exponent rules to our radicals because radicals are exponents. Apart from that, I believe that's it. I'm done. Email this to your grandma and I'll see you another time.